Thanks. Right, so yeah, I want to talk briefly about our strategy to send these NCPAs in our high contrast subsystem using a ZELDA sensor. So for those of you who do not know what a ZELDA sensor is, well, there are some great papers by Mamadou Ndiaye, Katie Doren, and Arthur Vigan. The first one, I think, from 2013. It has been exhaustively tested in the laboratory and on Sky in the VLT sphere. It was key to identify and characterize the low wind effect, like it was said in the previous talk. And it's a great sensor for coronagraphy since it has very high precision, down to the nanometer. And it works by using a phase shifting mask that is located in a focal plane. It phase shifts the wavefront by pi/2 in a 1 λ/d disk. And in a pupil plane that we form after that, you have transformed the wavefront aberrations into intensity aberrations, and you can retrieve the phase by applying a rather simple closed form relation, which is indicated on this slide. So in Harmony, we are facing the usual problem of having the turbulence, which is measured by a separate subsystem from the high contrast subsystem. It's done at a wavelength of about 0.8 microns, when our science is between 1.25 and 2.45 microns. And in Harmony, we don't have a correction of the atmospheric dispersion at the general level of the instrument. And so we expect to have not only classical NCPAs between the SCAO subsystem and the high contrast subsystem, but also quite strong chromatic errors because of that. And so we needed to implement a calibration unit for the NCPA that could be located as close as possible to the optics of the coronagraph. So in our case, it's a shape pupil, and which could analyze the light as close as possible in terms of wavelength from the science channel. So we pick the beam at around 1.17 micron, and we're going to analyze it in a 50 nanometers band around this wavelength. So you have a 3D view of the system, and the front-facing optics that you can see on this view are the one of the ZELDA sensor. So we use a CRED 2 camera, and the mask itself is supported by a 3D translation stage. So just a few words on the prototyping activities that we have at IPAG, together with LAM. So we have built some masks, and they are well, they meet the specifications that we set for them, and we have built first test bench to test the performance of the ZELDA sensor, and first to compare it with a known sensor, in our case a phasic sensor. And so the results that we have at the moment indicate that we have a pretty good agreement between the two measures, so down to the nanometer level. So we have a few differences between the two, but we believe that it's consistent with the precision of the phasic sensor, and also consistent with the fact that we have a fold mirror that introduces a few nanometers between the two sensors. So anyway, it's quite encouraging. So it was a first step that we wanted to complete. And by the way, that's the work of PhD students that has just started. So Adrien Ours, who is going to do his PhD around this topic. And then we have some other steps that we want to go into. So the first one is to simulate on this bench the residual dispersion that we'll have to live with, since we're actually going to implement a sort of passive ADC in the high contrast system. And it's going to reduce the dispersion that we have, but only by a certain amount. So we'll have to correct for a systematic phase that is induced by the residual dispersion, and we want to validate a strategy to reduce that in the lab. And the next step is going to replicate the residual SCAO aberrations. And so for that, we already have some data, which is provided by LAM, especially Elodie Choquet and Jean-François Sauvage, and we're going to use an SLM to do that. So we believe that these two steps are going to be implemented on the bench within the next few months. So stay tuned for a bit more results. Thank you. So if you have any question, of course, I'll be...
Excellent. Thank you very much. Let me see. Looks like we don't have any questions on the Slack channel just yet. So I have a question. You said that here, I can also turn on my video. So you said that you were planning to implement this with an SLM on the bench. Have you worked with SLMs previously for this kind of work, or will this be a first attempt with an SLM?
So for our lab, it's actually a first. We are used to DMs, but not SLMs. But actually, SLMs have been used at LAM on the meeting bench, which was a bench built around the ZELDA sensor, which was first developed at LAM. And SLM, well, one SLM was used for that. And I think that they're going to actually implement at least another one.
Okay. And what drove your choice for an SLM for this? Just out of curiosity.
Why did we chose an SLM rather than a DM, for instance?
Correct. Yeah.
Okay. Well, so in our case, we don't just want to implement the turbulence residuals. We also want to implement some quasi-static phase maps, and we actually want a bit more actuators than DM can achieve at the moment. So with an SLM, we have usually, at least 500 by 500 sort of actuators. We can go up to, I think, at least 1,000 or 2,000 on each axis. So we can get some very high spatial resolution structure with this type of device. But of course, there are some drawbacks, like, we have, of course, some of the polarization to take into account. And then we also have some possible issue with the frequency of the correction, or the frequency at which we can operate the device. But recently we found some SLMs from middle arcs, which can go up to, I think, 500 Hertz, but that's in the visible. And if you want to work in the near infrared, it's closer to 200 Hertz, which is still interesting, but yeah, it will be interesting to test that in the lab.
Certainly. And then I think we do have one question from Olivier asking if you can comment on how you center the ZELDA mask and make sure the centering is preserved throughout your measurements.
Right. So I didn't mention it, but actually in our design, we have the ability to place a lens between the ZELDA mask and the collimating lens here. And we use that to reform the image plane directly on the sensor. So we have the ability to look directly at the PSF itself, and we use that to first center the mask at least the first time. And then we believe that when closing the loop, we'll be able to use the tip tilt information to keep the star aligned. Yeah.
Okay, great, thank you. And then I think you answered one of our other questions on Slack, which is, again, talking about the SLM. You mentioned Meadowlark. We have a question from Deborah asking if that's an 8-bit or binary SLM.
If it's a what, sorry?
Sorry, an 8-bit or a binary SLM?
Oh, it's an 8-bit. I think so, yeah.
Okay.
If you want, in the other session, or on the Slack, I can give you the reference for this device.
Yeah, I think that'd be very interesting. All right, well, if there aren't any further questions, thank you so much. Really appreciate it. That was a great talk. And I think we will move on to the next one in the session.